Hello everyone, I'm Fabio Corti, and in this presentation I'm going to talk about the inductor SPICE modeling, including non-linearity due to non-uniform magnetic field. So here the content of the presentation. I'll start with a very brief introduction on the topic, then I move on the core loss estimation techniques that we analyzed in this paper. Then I focus the attention on the SPICE approach. I'll show you later the case study that we analyzed, in particular the buck converter, and finally some conclusion to summarize the obtained results. So let's start with the introduction. So a correct estimation of the magnetic component power losses simplifies the thermal design of the power circuit and at the same time allows for a correct estimation of the wall converter efficiency. This technique used to estimate the core losses can be substantially divided into two main groups. The first one is the finite element analysis approach, which has some advantages such as the possibility to have accurate estimation. On the other hand, it usually requires a long time of simulation and the results obtained is strictly related to the user experience. The other approach is the analytical expression and equivalent circuit. This approach allows for fast simulation results and creating a lumped circuit of the inductor, it is possible to understand how this interacts with a more complex circuit and estimate in a fast way the power losses due to both the ohmic losses and core losses. In this paper, we focus the attention on this approach. Let's move to the core loss estimation techniques. So the first technique that we take into account in this paper is the Steinitz equation. This is the well-known equation, which has as main advantages its simplicity. So it's very easy to carry out core losses estimation, but at the same time, this equation works only under sinusoidal and uniform induction. So the case of application are very limited, in particular in power electronics where the current can have waveform different from sinusoidal and very often. So this is a quite important limitation. For this reason, we decide to analyze the accuracy of also the improved generalized Steinitz equation, as shown here. In this, using this approach, we are able to obtain accurate estimation also under non-sinusoidal induction, but it works if the magnetic induction in the core is uniformly distributed, and this not always happens in power electronics. For this reason, in this paper, we propose a time domain core loss approach, which allows to estimate the core losses under non-sinusoidal and non-uniform field. In particular, this can be done using the field factor delta, which allows to map the current flowing through the inductor into the magnetic flux density, the effective magnetic flux density, which takes into account also the non-uniformity of the magnetic induction inside the core. In particular, on the bottom, you can see the equation which is valid for the toroid inductor, which have been studied in this paper. So the advantages coming from this approach can be summarized as follows. In particular, this approach allows for estimation under non-sinusoidal and non-uniform induction, is suitable for time domain simulation thanks to the wipeout rule, and finally is integrable in SPICE simulation. In particular, with this approach, it is possible to add a lumped circuit which represents the real behavior of the inductor, which takes into account also the non-uniformity of the induction, inside a SPICE circuit, so inside a more complex lumped circuit. So we analyze. So this is the case of study of these three different core losses estimation techniques. We in particular analyze a biconverter, in particular the inductor as shown in the figure. And of course, we also perform some experimental results where the main characteristics of the components of the biconverter are shown in the table. We focus the attention on the inductor. In particular, here you can see the main characteristics, so the permeability and the Steinitz parameters given by the manufacturer, and the characteristics of the inductor, so the number of turns and the geometry of the toroid. So starting from the material and geometry inductor information, we move on the estimation of the core losses with the three different approaches. In this slide is shown the approach used to estimate the core losses through the SPICE simulation. In particular, we measure the real current flowing through the inductor, starting from some geometry information. We obtain the magnetic field. And starting from the Steinitz coefficient and the permeability, first permeability curve, we were able to understand, to compute the effective magnetic flux density. This information were then used in order to estimate the time domain core losses. And making an average over a period, it was able to estimate the average core losses. So here you can see the experimental setup used to sense the current flowed through the inductor, and while on the table you can see the four different operating conditions under which the core losses have been estimated. So let's move to the conclusions section. So here are summarized the results obtained. On the left you can see the case A. In particular, you can see the current sensed from the on the inductor, flowing through the inductor, IL. You can see then the magnetic flux density, which have been computed online, so in a time domain manner. In particular, you can see two traces. The blue one is related to the field factor approach, so the proposed approach, while the red one is using the improved generalized Steinitz equation approach. Then you can see on the bottom the waveform of the core losses over time. Of course, if we made an average in a period, we are able to compute the average core losses. And finally, there is the BH curve related to the particular operating condition. All the results are summarized in table 5. In particular, we can see that the proposed approach allows usually for a higher estimation of core losses compared to the other approach. This is due to the fact that the proposed approach takes into account also the non-uniformity of the induction inside the core, which substantially produce an increment of the core losses. So, to conclude, in this paper, a comparison between different core losses estimation approaches have been proposed. Both the improved generalized Steinitz equation, the proposed approach, allows for a time domain estimation, which is a suitable solution to operate in SPICE environment, And finally, the proposed approach allows for more accurate estimation since it is able to take into account also the non-uniformity of the induction inside the core. Thank you for your attention.